So this will be one just a quick announcement of things to follow. First of all, because I finished regularization today, we'll have a next homework 2 weeks later. And we have a bunch of challenge. You can check out the challenge folder. The two things to announce. First of all, because I missed a class last Tuesday, we'll have to make up some time. And I'm also going to miss a class on December the 10th. I'll be traveling. So we'll also make up 2 classes after that in December. That's one thing. The second thing is decision tree and ensemble methods will be the final part I want to talk about on the statistical part, right, on the machine learning or statistical part. And then we'll move on to causal inference and econometrics side. Obviously, there are many interesting models that we can talk about in statistics and machine learning, including supported vector machines, neural networks. I will have all the lecture slides I've written on those topics on my website, but I will have no time to teach it. So you can, if you're interested, you can read them yourself. So decision tree, but decision tree is already fascinating. Okay, so we'll talk about decision tree and ensemble methods, which are very, very important. And then we're ready to move on to talk about causal inference. Okay, so what is a decision tree? Well, this is a decision tree. Let's say, I want to know how people decide. I want to know which county vote for Clinton or Obama. That's Hillary Clinton and Barack Obama in 2008 when they're running for the Democratic primary. So I want to know which county actually vote for Clinton or Obama. Well, I can use a decision tree. Okay. So the decision tree idea is, okay, let's first of all think about what is the most important factor. Now, by the way, this decision tree comes from the underlying statistical model, which the New York Times actually run. So New York Times using a decision tree to fit, they actually collect the data, the election data, and they fit it, okay? So the result is actually statistical estimate. It's not man-made. It's from the data fitting, right? That's so part of the reason why people used to love New York Times is because they would do something like this, right? Unfortunately, we don't have, Chinese newspapers don't run decision trees on data to tell you. Okay. Anyway, so it turns out the most important factor, at least in this case, for this tree, is whether the county is 20%, more than 20% black. If yes, they vote Barack Obama. If no, let's consider some other situation. Okay. First of all, let's think about what is the percentage of people who are highly educated. Actually, not highly, but at least they graduate from high school, right? Now this is actually a little strange to me, but if they're lower than 80% people graduate from high school, they vote Clinton. Predict Clinton. If more, let's think about somebody else, right? Is the high school graduating rate higher than 87%? Okay, so if it's higher than 80%, so if it's really high, if a lot of people graduate from high school, they vote for Barack Obama. So it looks like, at least in this primary election, highly educated people vote for Obama more. Okay, so the 80% vote for Obama. If there is if there's still no, then we ask whether they're in the South, in the Midwest, and if in the South or Northwest, they vote for Clinton. Midwest, if they're Midwest, then we still have more decision to make. So you can see the structure of decision tree is we start with we start with the decision and we say, okay, let's go here, right? If this condition is satisfied here, not satisfied in this direction, but even if they're not satisfied, then we still have different decision to go, right? Until we may reach a final prediction of whether it's Clinton or Obama. Okay, so that's the ideal of a decision tree, right? Although yeah, but then we got more to go. I forgot to post the entire tree here. Yeah, so what's more? Where's the county? How many households are poor? If there's more poor people, they also vote for Clinton. Density, and finally, some other decision. Okay, so you can take a read yourself. But that's an interesting application of decision trees. All right, so what is a decision tree anyway, right? So a decision tree is a statistical method. It's a statistical model, and the model is very simple. The idea is very simple, which is we just divide our x into all kinds of splits. Okay, so we take a look. So we start from. So this is a tree, right? This is a tree. A tree has this is called a node, and then for the node it goes down to some other nodes. It goes down to some other nodes. Then each node is called the children of their parent node. So this is the parent. This is the children. Okay. Now, in the end, if there's no other children, if we have reached the end, no further children, we call them the leaf node, in the sense that suppose this is a tree. Okay, so a tree the tree grow like this, but our tree grows like this. Okay, it grows upside down. So starting from the root, this is the root, and we start to grow the tree. So in the end, the final is called a leaf, right? The leaf is the top, the final end. This is called the root. This is called the root node. Okay, binary tree. Right. Okay, so why do we draw the tree upside down? Why not just standing up? Okay, so that has nothing to do with statistics or anything. That has to do with human aesthetics. Okay, we apparently people think that this is more pretty than the standing tree. Anyway, so the decision tree model is basically to start at the root, choose one of the x variables and say, okay, is x larger than this or is x smaller than this? If it's larger than this, let's go here. Smaller, let's go there. And then here we pick another x and say, is it larger, smaller, and then go on and on and on until finally we're confident that we're able to make a prediction, okay, which is belong to Clinton or Obama or something else. So that's a decision tree model. Okay. All right. So let's take another look at another example, right? So now here I'm going to predict the salary of people, baseball players. So we have two statistics. The one statistic is how many hits this person has had. The other statistic is how many years he has played. And I want to use the statistic to predict salary, right? Which is, I'm sorry. So these are observations. Now each yellow dot has a y value, which indicates the salary. But we're not saying. So to do the decision tree, we're essentially dividing this space, the x hits and the year space, into different regions, and then the prediction is essentially the average of the y's in this region. So let's look. Okay, suppose we have this model. It says if year is smaller than 4.5, I predict the person's salary is 5.11. I don't know maybe it's millions or whatever, right? So 5 million is my prediction if that person has less than 4 years of playing time. If he has more than 4 years, 4.5 years, then let's take a look at his hits. If he hasn't hit a lot, his salary will be, our prediction is 6 million. If it has hit a lot, our prediction is 6.74 million. So that's my model. Now, if you take a look at this tree model on this graph, then it should be easy to see that this 5.11, like this one here, is years smaller than 4.5. So for everybody with years smaller than 4.5, I have a single prediction. Okay? And then for people who have year more than 4.5, then I have to take a look at hits. If it hits more, okay, that's 464. This one. If it hits less, that's this number. So in other words, this tree model, if we represent this tree model in this, in this kind of graph, then essentially you can see the tree really is the effect of tree is to divide the space into 3 different regions. Okay, one region is year smaller than 4.5. One region is year larger than 4.5, but lower hits, and the other region is year, long years but more hits. So these 3 regions correspond to these 3 predictions. Right. Now these regions are called leaf because they are essentially the leaf. Okay, so this is a tree. This is the root. This is the leaf. Okay, this is the leaf. The leaf is the final prediction. So in the final prediction, we have 3 different leaf or 3 different regions that we have divided into. So a tree model. So what is a tree model? A tree model is essentially dividing our x space, because this is the space of x. We're just dividing the x space into many regions, and each region will be a leaf in our tree representation. Okay, right. So what does this remind you of? Because we have already studied this model actually, a very similar model to this one, right? Where we divide the x space into many regions, and in each region we fit something. What is that? Do people remember? We have already talked about it. Piecewise, exactly. So a tree model is a piecewise constant model. That's really, really simple. A tree is a piecewise model. Actually, to be more precise, a tree is a piecewise constant model. Because how do we make prediction? Like for the tree model, it's extremely simple. If I divide the X space into these three regions, how do I predict the salary of people in this region? I just average all of them. So the mean value, the mean of Y in this region is my prediction here, okay? Right here. So in other words, in each region, I just fit a constant. And the constant is the mean, right? The constant is the mean. Here I fit another constant, it's the mean. It's the mean. So the decision tree is a piecewise constant model. In each region, we fit a constant. And what is that constant? That constant is going to be the mean of the Y values in that region. Okay? All right, so we have already talked about it. So it's done. We're going to move on. No, not so quite. Okay, not so quite. For piecewise constant model, there's an important difference between tree and a piecewise constant model, which is for piecewise constant model, okay, what I'm doing is, let's say X is one dimensional, right? Okay, so we have a bunch of data like this. Now, if I want to do piecewise constant, my first step is to choose my cut points. So I want to cut here, and I want to cut here, okay? And if I make these two cuts, I divide the region into three regions, I'm going to fit a constant. So I'm going to fit a constant Y here, right? It's constant here. I'm going to fit a constant here. I'm going to fit a constant here. And the constant is what is this value? This is the mean of the Y value in this region, right? Okay, so this just like decision trees. But there's an important difference, which is this. In order to do piecewise constant, I have to decide where the cuts are. Okay, I have to decide where the cuts are. Now, people also talk about like threshold. In our TA session, we talk about threshold models. We have people discussing regression discontinuity designs and such. And when you're doing all these kind of threshold models, you have to pick the threshold. You have to pick the cut point. Okay, you have to pick it yourself. Now, is there any way to let data tell me where I should cut? Can we do that? That's the question. Okay. Why do I have to cut myself? Because I often don't know how to cut. Right? There's often no clear rationale how to cut. So I want a method to let data tell me how to cut it. All right. So maybe data says, look, at least for this, at least in here, it looks like it's better to have another cut here, because these data look like different patterns, right? Okay. Correct. So I want to look at the data, and let's say for this one, maybe we also divide it like this, one more cut, so that because these, then I can obtain a better fit here, I can obtain a better fit here, right? So I can let data tell me how to cut. So if I let data help me cut, this procedure is called adaptive procedure. Okay. So adaptive procedure means we let our model tell me how to do things. I will let data tell me how to do things. Let data tell me what my model looks like, not I determining what the model looks like. That's called adaptive methods. All right. Okay. So I believe that's the first adaptive methods we have introduced. Maybe, well, not quite. Forward stepwise regression is also a kind of adaptive method. But anyway, so this is if we do adaptive, if I let data tell us where to cut, that's essentially a tree. That's essentially a tree. The decision tree is a piecewise constant model that is adaptive. It's really simple, okay, in that way. But we are going to talk about how to do this in March. But the second point is, even just looking at this, right, without talking about details of regression of trees, just looking at this, like I said, I can cut here. It looks like it improved a little bit. I can cut here. Looks like improve. I can cut here. Looks like improve it. But I can always do this more, right? What about just I just make a cut everywhere? Just for every data point, I make a cut, and I just predict my Y to be that data point, right? Every place I just predict Y to be that data point. Then I'm going to have in-sample error equal to 0, right? Is that so? How do I do this? Now you clearly know this is not the best right now. Right? So how do we do it? Right, so I want to let data to let me cut. I want data to tell me how to cut, but I don't want to do it. Because data is not that smart, right? So if I just let data say, okay, whatever fits better, just cut there. If I tell the data to do that, the data will cut everywhere, and just make it a sample size equal to 0. So what should we do? So the idea of tree is actually very, very simple. I'm choosing to cut as long as I can improve my fit, right? Improve my fit. But I should only cut until what? If you are imagine if you are going to design a procedure, how do you design it? One way is very simple, right? So without this cut here, I have some data points here, some data points here. So data can tell me, look, if I cut here, then obviously I can improve my fit, because without this cut, my fit is here. After the cut, I'm fitting my data much better. So my in-sample error goes down. But obviously, this cannot be my only criteria, because then I'll just go all the way down to 0. So how should I do this? Remember how we do in model selection? In like forward. Do you remember how we do forward stepwise? When we do forward stepwise, we start with no variables. We add a variable, add a variable, add a variable. Remember you can always add a variable, and the in-sample will go down, or at least not go up. But we do not really always add. We stop somewhere. In this case, how should we stop? What should I use to guide me? Well, the underlying idea is pretty simple. I should stop when the out-of-sample error starts to increase, right? Because you can always decrease your in-sample error. But the out-of-sample error will have, ultimately, the out-of-sample error will have what? Will have a U-shaped curve, okay? So the idea behind all these algorithms is the same, that we should always try to stop when this is the minimum. But how do we do that? Well, there are many different ways. There are many different tree algorithms, okay? So we'll talk about some of the most popular ones. But the underlying idea is always to do this. And the underlying simplest idea is always the same, which is when we are cutting, when you cut, your goal is to improve the in-sample fit, but you should always also estimate the out-of-sample error, like some kind of cross-validation you can do by dividing your data into a sample and a validation, right? Training and validation. You can do cross-validation and use cross-validation to figure out what your out-of-sample error is. So you should continue to cut, not as long as you are improving in-sample fit, but as long as you're improving your out-of-sample fit, okay? The out-of-sample error, or the test error, or the validation error, whatever you call it, okay? So that is basic gist of trees. So if you understand this, you understand trees, what trees is about. And then we can go down to more detail about, mathematical representation and how to actually execute it in reality, okay? All right. So let's see, some more details, right? First we begin, now you can use a tree to do regression and a classification. This is a general method, right? So we start with the regression. Now, if we do regression, it's called a regression tree. We start with the data. D is equal to y and x, right? Yes, x can be multi-dimensional. It doesn't have to be one-dimensional. Y is typically one-dimensional. It's your target. The goal of the regression tree model is by cutting, we will be successfully divide our X region, the predictor region, into M different regions. Okay? So M is the number of regions we end up cutting the space into. Right? So in the end, what is my model? My model is very simple. My model is in every region, my prediction is the mean of the Y value in that region. And that's it, okay? I just cut into M regions. In every region, I just predict the mean. That's my regression tree. Right? So my function f, okay, this is my fit, is simply the my prediction for every region, which is the mean y in every region, and sum together, okay? Sum together, right? So depending on where my x is, my prediction of a certain x value is essentially the mean value of y in that region, okay? In the region where the x is located. And that's my regression tree model. Okay? Like I said, it's a piecewise constant. Now, how do we actually build it? How do we estimate the regression tree? Well, we cut, but when we cut, what is our criteria for cutting? Right? the criteria should be, like I said, should be improving the ultimate criteria is improving out of sample fit. But let's just pretend we're only improving in sample fit first, okay? All right. So, suppose this is our data. All right. Now, if I do not cut, what is my L2 loss? Because we're talking about regression tree. So for regression tree, we use the L2 loss function, right? Now, so the L2 loss is y minus y hat, okay? Square, right? That's the L2. But what is the y hat? Well, if without cutting, my y hat, in this case, is this, okay? This is my y hat without cutting. But let's say, okay, suppose I cut here. Suppose I cut, let me just cut here, okay? Suppose I cut here. What is y hat? I have a y hat here. This is my y hat for this region, right? For this region. Okay. Some points here. Points here. What is my y hat for the second region? It will be, remember y hat is always a constant, so the mean of these. So it will be somewhere like something like this, okay? Y hat in this region. So I can calculate the in-sample error for this one, right? Which is these points minus the y hat square, plus these points minus the y hat square, right? All these points, correct? Okay. So then I can calculate the in-sample error this way. I can also try to cut it a slightly different way, right? Which is, I think everybody wants to cut. So I think everybody wants to cut here, all right? Okay, everybody wants to cut here. If I cut here, then my y hat, my y hat will be here in this region, and in this region it will be y bar, okay? So I can calculate the in-sample error of all three, especially the two. So I'm considering what I want to cut, right? So I want to compare all these. Which one is the best? Which one is the best? Clearly the green is the best. It fits the data the best. So that means I should cut here, okay? I'll cut here. All right. And then after I cut here, what do I do? Then I go to the next step. I consider what I want to cut more, okay? So here's the idea, all right? Now let's go to a second. Let's go to x1, x2, right? x1, x2. So the x1, x2, they are two dimension, and the y is this region. Okay, so we have all different kind of y's, etc. I'm just going to be really sloppy here, but the idea is I first decided where to cut. Suppose I'm on x1, I decided where to cut. I made a cut. The second step is I choose one of the region, okay? Maybe I pick this region. And I consider, okay, what I want to cut here. Suppose now I'm cutting along the x2 dimension. Then I just say, okay, should I cut here? Should I cut here? Should I cut here? I pick one that's the best, and I cut here. And then I again choose one of the region. Okay, you can randomly choose. You can choose one of the regions. Suppose I pick this one. So for this region, again, based on the data, I will cut here, okay? And then on and on and on. You can just go on, okay? Just go on. Continue. That's basically the adaptive cutting process. In every step, the goal is to improve the what? Improve the L2 loss function or the RSS in this region. So when I consider when I want to cut, if I want to cut in this region, like here, my goal is to test all the different ways of cutting until I find one that minimize the RSS. Okay, minimize the y minus y bar, y hat square in this region. Okay, in this region. Suppose that's here. That's what we're doing. All right. Okay. Now, I just said that if we only look at the in-sample loss and we use it as a cutting criteria, that's not good, because we should care about the out-of-sample, not the in-sample. So there are different ways to do this. Okay, there are different ways to do this. One way I'm talking about here is called the CART algorithm, which is one of the more popular algorithms to do the trees. In the CART algorithm, when we're cutting, we don't think about the out of sample. Okay, we just think about in sample. So we just care about how much my model can fit in sample, and then it's cut until what? Until like you decide a stopping criteria. You can say until the number of data points in each region is smaller than 5. Okay, like five data points, and then we stop. You can define a stopping criteria. Right, so in that case, we grow a very extremely large tree. Right, and the tree is going to overlarge. It's going to overfit. Because it fits, it cuts too much, okay? It fits data too much. And then what I'm going to do is I'm going to go back, okay? I'm going to cut the tree to its proper size, guided by cross-validation for out-of-sample error, right? So that cutting back process is called, so that's the funny thing, right? Because we're using the tree analogy. So, the final one is called leaf. This is called node. This is called a root, and there's a leaf. So the CART algorithm is that we grow a very large tree, okay, by just not thinking about out of sample, just trying to improve in sample fit, and then once we have a large tree, we're going to cut it back. But what is the term for cutting back a large tree in gardening? Like in gardening, what do you do to a tree? You prune it, okay, right? You prune it. So the gardener would prune the tree. So here we use the same analogy. We're going to say we're going to prune the large tree by essentially shrinking the tree to a smaller size, guided by cross-validation. Okay? So essentially what we're doing is this. We're minimizing, so after we have grown a large tree, we're going to minimize our sample error subject to a regularization term. This regularization term is alpha times the size of the tree. Okay? So we're minimizing this. Right? And then this alpha is large, and this alpha is our tuning parameter, right? It's the Hopper parameter, just like the lambda in lasso and the ridge. So we're going to fit this new objective function, and using cross-validation to find out the optimal alpha. And by doing so, we shrink the tree smaller and smaller, okay, to produce a tree that has the best out-of-sample performance. All right. Okay. So the detailed algorithm is here. You can take a look, but that's essentially what I just described. Here is an unpruned tree, right? This is the tree we're using the same baseball salary where we have hits. Well, actually, the baseball salary example, the data contains many variables other than hits and years. There's also basically there's some other variables, okay, for baseball players. Now, if we do not prune the tree, if we just grow a very large tree, just stopping until some stopping criteria using the CART algorithm, we're just improving the in-sample fit, then we end up with a very large tree. And then we prune it back by regularizing. Okay? By regularizing, we put a penalty on tree size. Tree size just means how many leaves we have. Okay, how many leaves we have. So we penalize tree size by putting a penalty on it, and we fit the tree again using cross-validation, and the result is the result is this extremely simple tree at the beginning, right? So this is after pruning. So we grow a large tree and go back and cut it back. This is the result for cross-validation. Okay. So our cross-validation error is this green line where we find the optimal point to be here. Okay. The optimal point, which is 1, 2, 3, which is our tree size equal to 3, meaning we should have 3 leaves. Okay, 3 leaves is here. That's our optimal point. Otherwise, the validation error goes down. The training error always goes down like this. So you can grow as you grow the larger, if your tree become larger. When your tree become larger, simply means you are cutting and cutting and cutting. Okay, just continue cutting. You continue to cut, your tree become larger, and then the training error always go down, but the validation error will go up like this. The optimal size is t equal to 3. Let's go back to see this right. Look at here. The optimal tree is 3. Okay, 3 leaf only 3 leaf. Here only 3 regions. That's our after pruning. We'll bring it back to 3 regions or 3 leaves. Okay, so that's it. That's regression trees. Extremely simple. Next time we're talking about classification trees, which is also the same idea, slightly more interesting. I think we're out of time today. So let's stop here and continue on Thursday. Okay.